Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm John Boylan, and I coordinate this series as well as some as the other Studio99 efforts with some of the Studio99 stalwarts. This afternoon we have Thomas Deuel, who is a neurologist, neuroscientist, and sound artist. Currently works with the Swedish Neuroscience Institute, as well as being an affiliate professor at the University of Washington's DX Arts, Digital and Experimental Arts program. And we brought Thomas to talk about the project, the work he's been doing using electroencephalograph, electroencephalograph to generate sound and music in a term he's calling the encephalophone. So anyway, that's about it for me. Thomas.
So I'll be talking to you about the encephalophone. So it's a musical instrument that I have been working on that's driven by thought using EEG, or electroencephalogram. I'll tell you a little bit about EEG in general and how it works. I'll talk a bit about the history of people taking EEG and turning it into sound and music, and then I'll talk to you about my device more specifically, and then I have some videos with demonstrations. And feel free to ask questions along the way. I'll get fairly technical, I can get more technical, I can get less technical. Stop me and feel free to interject. So just relevant personal background, John touched over this a little bit, but the things that brought me to this place to create this device are my main job is I'm a neurologist. I'm with the stroke team at Swedish Neuroscience Institute, and I also read EEGs for them with the epilepsy group. I have a PhD in neuroscience, and most recently in my postdoctoral work, I've been working on processing of complex sound, and specifically music, the cognitive process. I also am an amateur musician, and I have a certificate in music composition from New England Conservatory, and I practice as a sound artist, mostly doing audio installation artwork and field recordings. And then I have a studio/laboratory. I just call it a studio lab because it's really halfway between laboratory and art studio. Kind of combines these things at Inscape Arts, which is in the International District here. I'm also an affiliate professor in digital arts and experimental art, the DX Arts program at UW, and I teach a class called Art and Brain, and there's an Art and Brain laboratory that we have there as well. So it's a whole lot of parts, and all these parts kind of come together in this the development of this device. I call it Encephalophone. So it's a novel musical instrument. It generates musical notes from conscious control without movement in real time. It uses EEG, which I'll talk about some more, and it uses intentional control, which is different, as I'll show you, than people's developments in the past with EEG. Rather than sort of a passive generation of music, you can actually control it consciously and intentionally in real time. So essentially, you control the music with your thoughts. And I have a patent pending on the device. So EEG, it's a medical diagnostic technique. It reads electrical brainwaves. Brainwaves would be a colloquial term, but it just reads the electrical activity of the brain. It uses metal electrodes in a conductive gel placed on the scalp. That's me with an EEG cap on. It was developed to diagnose epilepsy, and it's still how it's used primarily, and sleep disorders, and it's also used increasingly in neuroscience research. So its advantages are it's very fast response, so millisecond response. It's also non-invasive in this format. You put a cap or electrodes with gel on your head, and it's very non-invasive. There is invasive EEG, and we do that in the hospital for intractable epilepsy patients, where we'll cut their skull open and place electrodes either implanted or placed directly on the brain, and the signal is much better than it is here, but I wouldn't go and do that to you to help just to generate music. But in general, this format, the Scalp EEG, is very non-invasive, so I don't have to inject any drugs or give you any radioactive tracers to measure. Disadvantages are the localization is pretty poor. We can kind of tell what general region of the brain, but specific localization is not very good. We can't get down to millimeter resolution, not until we get intracranial, when we cut the skull open. But in this format, not great localization. And also there's a lot of noise from non-brain signals. So when we're listening to I use sound metaphors a lot, but when we're listening to the brain electrically at the scalp, it's quite quiet. We're talking about microvolt signal, 2 to 100 or so microvolts are the typical ranges. Around there's all kinds of non-brain signal that can drown out EEG. So you have to listen very carefully. It would be like being in a loud party and you're talking to somebody who has a very soft voice. You have to either get in another room and get all the other people out of the way, or get really close to them and just tune everything else out in order to hear it. So that's a big disadvantage of EEG, scalp EEG. So what it's measuring is synchronous activity of many neurons, many nerve cells at once, not one or two, but thousands. That's what's required to measure at all. If you have 100 neurons, you're not going to measure that at the scalp. And it's estimated that you need approximately 6 square centimeters of surface of the cortex in order to actually get a signal. To top that off, these signals are volume conducted through CSF, the cerebral spinal fluid, and the meninges, the coverings of the brain, and the skull, and then the scalp and skin, and all that. So that attenuates the signal. So then by the time you get out here, the signals that you're measuring are in the range of 2 to 200 microvolts. And then there's all these non-brain signals that I talked about that can cause artifact, and they can cause misinterpretation, and they often do, of EEG signals. So muscle, for one, if the muscles of mastication, of swallowing, if you all bite down, you notice there's the masseter right here pops out, and then even the temporalis, it's this muscle all the way up here, and if you bite down, you can feel it all the way up here. There's some muscle activating. That's millivolt range, so 1,000 times stronger signal. So if you're chewing, you're talking, you're biting down, it's going to drown out the EEG signal. Other things, there's the orbit of the eye. So when you blink, you move your eyes around, there's a big dipole, and that gets measured. So that's another source of error. The tongue itself has a big dipole. So if you're talking, if you're chewing, again, it'll cause noise. So where are you measuring them? You're really measuring, when you're measuring at the scalp, you're measuring voltage potentials of charge movement across these neuronal membranes, across these cells of many neurons at once. Again, on the order of thousands are required at minimum. It's the recorded EEG is generated by the cortex, so it's only the surface of the brain. You're not measuring deep structures at all. And to top it off, the signal needs to be perpendicular to the scalp. So there are all kinds of nerve cells that are pointing in different directions, and you're only measuring the ones that are pointing to the scalp. And you're summing off these things called EPSPs and IPSPs. They're postsynaptic potentials. You're not measuring action potentials, which are what people often think of when they think of communication between neurons. So why is all that important? Well, the thing is you're really only measuring a subset of the whole electrical activity of the brain, a small subset. So that makes interpretation difficult. So we use this international system for placing the electrodes so that everywhere in the world is the same. If I read an EEG from Istanbul or from Shanghai or from Wenatchee, I'm going to have the same format come out. So I'll know what electrode is what part of the brain. So we use anatomical landmarks. So the inion, which is this little, you can feel it in the back of your skull. There's a little protuberance out there in the occiput. That's the inion. And then the nasion is this low point in the nose where people's glasses, the bridges. All the electrodes are placed with percentages of that circumference, or half circumference. And it's called the International 10-20 electrode system because they're 10 and 20% of these various distances. Even numbers are on the right, odd numbers are on the left, and then their regions of brain are labeled as well. So F is frontal, C is central, T is temporal, P parietal, O occipital, so that you have you know where you're at. And this is the very very, very standardized around the world system. Then you have electrodes. Each of them are measuring voltages, and then, as I'm sure you all know, you measure voltages as potential differences. So it's something. It's a voltage relative to another voltage. It could be relative to ground. It could be relative to another electrode. So there are different montages that you use. You can measure one next to another. So bipolar montage is a very popular one. You're measuring the voltage of one electrode to the one adjacent to it, and that's what we will mostly be looking at. You can do a referential where they're all related to one. You can have a sort of it's not truly a ground, but a reference on the forehead or on the neck, and all the other electrodes are referenced to that. This is what a normal EEG looks like. This is one of the bipolar montages. So what we're looking at is a whole lot of squiggly lines, but going across the page is time. So on the x-axis, that's about 10 seconds going across. And each one of these essentially represents a single electrode. They're one relative to the other, as I mentioned, but this is about 20 electrodes. They're going across. And as you can see, there's some periodic activity. There's some regular waveforms that are coming in a periodic fashion. They're not just, there's some variation, obviously, but you can see some regular frequencies coming in there. So we take all that and we divide it up into these frequency ranges. The slowest, they're pretty arbitrary, honestly. They're just categories of frequency ranges to help us sort them out. The slowest are called the delta, up to 4 hertz, and then 4 to 8 is theta, and then alpha and beta, and then there's gamma, which is even faster. And the general rule is as you go down to the slower, that's the more sleep and less wakefulness and less attentiveness, and as you go up, it's more attentive. And that part of the brain is more active in general. That's the general rule. There are exceptions. This is another normal EEG, and there's some interesting patterns here. On the left, it gets the same setup. So this is about 10 seconds, and about each one of these squiggly lines is a different electrode. On the left, the subject has their eyes open, and then they close their eyes. And these are some normal patterns. So with their eyes open, we have these things with the black arrows called lambda waves. Those are waves that appear in the visual cortex in the back of the brain when it's very active and it's looking around. So if you're reading a book or scanning or looking up at the ceiling, those lambda waves will come out. It means your eyes are open and you're scanning something actively. And then you can probably see a big dip right in the middle. Not the red arrows, but right to the left. That's the eye. So that's that artifact I was talking about. The eye closes. Every time you close your eyes, you have something called the Bell's phenomenon. Your eyes actually go up. So you close your eyes, you blink. Even when you blink, your eyes go up and they come back down. It's a reflex. You can't help it. You may not believe me, but it happens. So as that goes up, the dipole between the cornea and the retina causes a big deflection. So that's a source of error, that big dip. But then after it, you see this fast alpha frequency. So it's around 10 hertz there. That's the red arrows. So that's, again, the visual cortex, but now with the eyes closed, it's no longer receiving input like it was over on the left. And it's resting. It's sort of a holding pattern. It's that part of the brain saying, I'm here, I'm ready, I'm awake, but there's no input. Even if you're thinking, you're not going to, you're thinking about imagery. So people ask this often. If your eyes are closed and you're just imagining things, you still get this resting. You won't get that active scanning type of pattern. Other normal patterns, there's something called the P300. It's an event-related potential. So this is a pattern that basically recognizes novelty. It could be a visual novelty. It could be an auditory novelty. It could be tactile. So all of a sudden, an elephant appears, and you'd get a P300 because it's new. You haven't seen this elephant before. And then I go back and I show you the elephant again, and you get another P300. Around the third time, the P300 will go away because it's no longer novel. It's really a novelty kind of detector. Or I should rather say it's not it represents the detection of novelty rather than it's a detector. Then you kind of get used to the elephant. The elephant's no longer new and interesting, and the brain gets very bored quickly with things that get repeated. But then if all of a sudden I show up, there's a monkey, then boom, you'll get another P300. And then the monkey comes back, maybe another one, and then maybe the third time, the monkey's no longer interesting anymore. Then if I go back to the elephant, now the elephant's new again, so you'll get another P300. That's how it works. It's a normal signal. It's the reason I bring it up is people use that as a trigger for various things, for control of devices and with EEG. So I mentioned a lot of this noise. Probably don't need to go over all of it again, but just to give you some examples. On the left, that picture of those big deflection, that's the eye again. When you blink, you get this huge deflection. But other sources of noise can be just poor conductance. You don't have good gel contact between the electrode and the scalp, or electrical noise, cell phones nearby, other electronics in the hospital will have IV pumps and things, and the electrical noise can be a problem because these are very sensitive electrodes with high dynamic range. Muscle, so I mentioned like the chewing muscle up here in the temporalis. That's what's going on there. So all that red, very fast activity that just looks like a big red smear at the top of that. That's all muscle. So you can imagine trying to read underneath that is pretty darn difficult. It's a big source of problem. So people have to be kind of quiet, not using their muscles. Even just standing up with an EEG on, the muscles that are keeping your head up, that are propping up, the neck muscles just propping up your head, they'll create a lot of noise. So the best way to get a good reading is to have someone laying down and quiet and not chewing and not talking. And then another issue is, of course, that besides the fact we have all this noise, a lot of these signals we recognize as patterns, and we have a general sense of what they represent, but we don't know what a lot of the rhythms mean, quite honestly. So people have been trying to harness EEG for creating devices that control things for a long time, so brain-computer interfaces. I really need to update that photo. That's like a 1982 monitor, but that's a stock photo. So the idea of a brain-computer interface is a direct communication between the brain and the computer, and you might use it to restore or even augment cognitive or motor functions. So restore in the sense of someone who's got motor disability, augment in the sense of a normal person who could control things without moving. And we've been researching this for 50 years or so. Started at UCLA under a grant from DARPA, but BCI research has been going on for a very long time now, almost 50 years. And even after 50 years, we're kind of bumping up against the limits of the technology of EEG. And the best groups really achieve about 75% accuracy with a lot of training, really good protocols. So why does that happen? It's because of all the things I was telling you about with the artifact, the noise, and then to top it off, the lack of specificity. We don't know what a lot of this means. There are very few signals that we actually know the meaning of. Yeah?
In general, if you were willing to be invasive and drill holes in people's skulls and stick electrodes wherever you wanted to, would almost all of these problems go away?
A lot of them do. We then have a whole nother body of knowledge we need to acquire with very few subjects. Because I worked with, so I did a fellowship in surgical epilepsy at Harborview, and one of the reasons I went there was because they did a lot of surgical epilepsy. So we did a lot of this. Probably one of the biggest centers in the world for.
So in theory, if somebody was really wanted to do this.
Jeff Ogeman, who's the neurosurgeon I worked with, also worked on brain-computer interfaces intracranially. But the basic answer is yes. What makes it complicated is the number of people that you can imagine. Yeah, it's very invasive. That's not the purpose of why we cut their skull open in the first place. We're trying to find out where their focus of epilepsy is so that we can take out the smallest piece of brain possible. And then we have to consent these people, so you can imagine the ethical barriers. Do you mind if I make some music out of these electrodes that are implanted in your brain in surgery? Well, don't worry, we'll still take care of your epilepsy. But we can actually ethically consent people, but access is very difficult. This is one of the reasons I was doing research there, is because I had access to patients who will consent while they're still awake, and yeah. But the basic answer is yes. The noise goes away, But then we still have that specificity problem, like we have a.
You gotta figure it in, you're not gonna figure it out.
Exactly. Yeah.
But the William Gibson model, from, I guess the first novel, where you actually plug in with a jack, you have to still have full access to the brain, don't you? You couldn't just jack it in.
Well, not necessarily, because you could. You don't have to. There, we generally are using triggers from a very specific part of the brain, so you don't necessarily need the whole access to the whole thing. Yeah, and we'd have patients who have electrodes coming out of their skull, and they're able to walk around. They stay in the hospital while that happens, but they can walk around, go through their room. They're talking, they're awake, and they have they have electrodes coming directly out of their brain. Wow. Yeah, believe me, that would it'd be a lot better that way. And ethically, it's actually I'll talk about it later, but I'm using this not only to generate music, but also for cognitive rehab and for neurological rehab, and for those people, that might be a very ethical use of that technology. So people have been doing turning EEG into sound and music since the very beginning of EEG, really. So 1929 was the earliest description. This guy Hans Berger, and a few like weeks ago, I noticed that there's this strange piece of brain in this photo. This is the only photo I have of Hans Berger. It's a little disturbing, but he was the first one to describe EEG, and then 1934, these guys, Adrian and Matthews, replicated his results. And while they were doing that, they tried, well, let's try monitoring our own EEG with sound. Maybe we can just hear things. So very early on, people were doing this, trying to convert it into sound. And artists have been trying to convert EEG into sound and music for art pieces for a very long time. And one of the earlier famous ones was Alvin Lucier, the composer, who had a piece called Music for Solo Performer. And he essentially was looking at the posterior dominant rhythm, so that sort of resting rhythm that's in the back of the brain when your eyes are closed but you're not actively using your visual cortex. It turns on when you close your eyes, quite simply. He was using that to drive percussion instruments, so timpani and various other instruments, in this performance called Music for Solo Performer. He collaborated with John Cage, and it was a great piece conceptually, but in practice, what really happened was he's sitting up. He had a lot of noise. He didn't have good referential. It's not very good signal. And John Cage was watching the signal coming out and realizing in real time that it's not working so well. So John Cage kind of cheated and adjusted the levels. It made for a good performance, but it wasn't scientifically very tight. I'll just put it that way. This is a really long video, but there's part of the performance was the preparation, and so I won't go through the whole thing. But, there'll be some others I can show you. People continue doing variations of this. This was David Rosenboom did some pieces in the 70s. This one called Ecology of the Skin. We don't have a recording of this one. We have a schematic, but and a description, which I don't even quite understand. But it was called Ecology of the Skin. This is a direct quote: brain signals of multiple participants controlling mixing of music played by keyboard performers along with phosphene visuals. I actually don't know what that means, but
when you close your eyes, you get these like kind of symbols, right? If you push hard on your eyes, or if you have sensory deprivation,
yeah,
it's like a natural geometric patterns that your eyes create.
This was somehow phosphene visuals for the viewers. So who knows? But anyway, he did another piece later called On Being Invisible, and this one was a little better described, and we have recordings of it. So it was a self-organizing multimedia performance using event-related potentials from two performers' brains. So event-related potentials are things like the P300 that I showed you earlier. It's exactly what it sounds like. It's a potential. It's a voltage that you'll see with some particular event. But one of the more common ones that people use is the P300. So the first one was more sound, just sound. Let's see. Maybe I will. go this way to make this happen. Two, he used more human voice.
It has rallied
thus emerged a national dilemma and contradiction, and for him, a
the memory of
profoundly
its
personal
sensation.
Not sure why those aren't playing under full screen. And people have continued to try to make music and sound from EEG. A big proponent of this, who's done a lot of work, is a composer at the University of Plymouth in the UK, Eduardo Miranda, who's on most of these papers. So he's used some sort of, a lot of them are passive control, where you take a recording and then transform it into music in some way. One he used that was a little more closer to control, although not actually technically good control, was this using alpha versus beta rhythms. The beta is a little more attentive, and the alpha would be a little more resting. Yeah.
These pieces replicable.
It depends. I mean, the ones that are recorded and then you do post hoc analysis, sure, you could replicate them. Some of them are live, real time, and so they're improvisational, so you can't quite. But you probably could go back and figure out how to do music for solo performer. That's replicable. But I mean, of course, it wouldn't be the exact same as the original performance. But does that answer your question? I'm not.
Yeah, my question is just like, if like I have a second performer, so could he at least produce something similar as the first one?
Meaning, you play some passage of music, and then someone else tries to replicate it.
Right. Like differentiate that from random noise.
That would be theoretically possible. It would require really good control and very tight control and a lot of skill on the performer.
Right, because I think like
in these settings, no. The answer is no.
Right. The deep question is like ultimately, so even if like the device just captures the noise, the noise could like make it generate the music. So how do you know whether the music is a result of the noise signal or?
That's a very good question, and easy for me to be critical of others, but there's big problems with noise in a lot of these papers here. They haven't shown that they're very specific control. That's proven accuracy. So I'll talk a little bit about my device, but I've attempted to do that, try to demonstrate, prove that it's actually accurate and you have actual control, real control. These guys in the bottom at Stanford did a pretty interesting thing. Again, this is not control, but it's they took seizures and did a transform that made it sound like human voices, and you can kind of hear the whole evolution of the seizure go through. It's quite impressive. So then my device is new for a few reasons. One is one of the things you brought up, but it's a new musical instrument and a cognitive therapy device. I did it in collaboration with my research collaborator and my postdoctoral work, who's Felix Darvas. He's a physicist at UW in the Department of Neurosurgery. I have a patent pending on it. Its rationale is that, we can only get 75% control over, say, a robot arm, which is not good enough. If you're paralyzed and I hook you up to a robot arm with your brain and you only get 75% control, you can see why that would be not good enough. And we haven't really gotten much higher than that. That's not good enough for a robot arm, but it might be good enough for music, as long as it doesn't sound bad, and that 25% of the time it's not horrible. As long as you get a sense that you have some kind of control, even if it's not perfect, it could be good enough. So the idea is music is created with cognitively inducible signals, meaning conscious control, without moving. The signals themselves, people often ask, are you thinking about music? They're not musical in origin. I'm using motor and visual cortex to trigger the signal. So you're activating and deactivating motor cortex and visual cortex. We're not good enough yet. I do research on, on how we process music, cognitive processing of music. We don't know the signals well enough. I can't just look at an EEG of your brain and say, you're thinking about E sharp, you're thinking about B flat, and we're not even close to that. So that's not the signal we're using, but in the future, with better research, we may be able to get to that point where you're actually thinking about music and then making music. But this is really a transform between thinking about something else and turning it into music. So my goals were initially just creative. They were just to create a novel musical instrument that would be interesting, a new performance and composition and soloing device. But naturally, since I work with patients with motor disability, with stroke patients with ALS, spinal cord injury, I think of how could I use this to apply to help people with motor disability. So my goals are really in two directions. One is creative and musical, and the other is neuro-rehabilitative, is the way I'd put it. So we took our device and we have run some experiments, which we're on the verge of submitting. And essentially what we did was we wanted to just prove very simply that we have accuracy with this device. It's not just, I could attach a cap to your head and have music come out and I could convince you that it's working, but it would be very hard for a novice or someone else to say, oh, that's working or it's not. So what we do is we take the signal power from either visual or motor cortex. We run two different paradigms. We convert the signal power from that part of the brain into a musical scale. And then what happens is once we've done this calibration and we've converted into the musical scale, the calibration takes about 5 minutes. So we calibrate for each individual for each session. So even me, I'll redo it every single time so that it's specific to that person's brain, the position of the electrodes, everything. Then you're generating notes. Right now it's generating notes on a scale by activating or deactivating the motor and visual cortex. So you go through this training and the training's very brief, about 5 minutes. And then we test the accuracy. What we do is we give people a target note and we say, you give them 10 seconds to hit that note. They actually have to hit it 3 times in a row. We didn't want them to hit it once because if they hit it once, it could be random. But you have to hit 3 times in a row and then you score a hit. If 10 seconds go by and you haven't scored a hit, it plays a tritone like a bah, and you get another note and you get to try again. And you try to score as many hits as you can within a 5-minute trial period. So we just see how many times people can hit. And the goal was simply to see if we could do better than random. So our initial results, this is from 13 people. We're now up to 17 or so, but it's similar. It's actually a little better now. But random is down there on the right, and the average is every single person did better than random. These are novices, mind you. They haven't been trained on this at all. The average was much higher than random. Percentage-wise, it's not amazing, but we're up into 70% or so. We have the two conditions, the visual cortex on the top and the motor cortex on the bottom. The motor cortex is a little more difficult, but a little more interesting because it doesn't require any movement. You can do it with no movement at all. The visual cortex, you still need to open and close your eyes, which is movement in one way, even if we're not measuring the actual eye movement. But people did better than average, and they did significantly better than average. And that's basically all we were trying to prove here. We are doing experiments where we're going to train them and see how much better they can get with a good feedback loop and a good training paradigm. And my theory is that by using music, and specifically by using music and not using, say, a cursor on a screen that you're trying to just move left or right, that paradigm of music is powerful enough in the human development and in our cognitive space that I think it's going to be a more powerful feedback loop. And I think we're actually going to be able to do better than has been done in the past, that 75%, with just moving a cursor on a screen, because the feedback loop is music specifically. I may be wrong, but we'll see. We also did a skew bias to try to make sure that people weren't all just generating one note, and then they would always hit that one note just by chance. And some people were skewed from one side to the other. But overall, the skew bias was pretty minimal, and it was, we also did a separate analysis to say, okay, if you're always hitting this one note, what would be the chances of scoring as you did? And everyone did better. There was one or two that were very skewed, but for the most part, they weren't. And then performance-wise, we've performed this once in a audio art festival down in San Francisco called the Megapolis Audio Art Festival. And we had a band, and I was playing the encephalophone, and we had 3 other instruments. We had drums, we had bass, and we had guitar, and played 4 songs, and I gave a brief talk that was similar to this, but like a lot more simple, to describe what was going on. And then we just played 4 songs where I improvised. And I had a crazy get-up. This is an art festival, so I had a goofy wig on top of
A little sound check.
So at the beginning, so I still have to go through the calibration every time, like I said. The band decided to just kind of vamp while I'm doing the calibration. Saying on, off, that's the cued part of the calibration. And then once it's calibrated, we start playing. I'm the vibraphone type of sound. And the way it's set up right now, there's continuous notes coming out. There's no stopping it. So for a performance standpoint, we decided to use a volume pedal. That's why my left leg is up there like that, to allow some phrasing. They're just continual notes. It's not very interesting musically. You want to add some rests and some pauses. But I'm the vibraphone. I'm controlling the pitch. Yep. And here it's restricted to 6 notes. It's a pentatonic scale.
Welcome to our little show here.
With,
so we're
with 1 octave.
Dr. Gyrus and the electric sulci. And
then I do
what the hell is
a
going
brief
on. So I'm going to try to explain it to you now.
Discussion that's
so
similar to this
I'm going to talk to you a little bit about
and
this
there's a couple other songs.
Invention I made.
So
which is called
we're able
the
to
Encephalophone. And
switch.
it's a
You know, I
musical
switched
instrument that you
keys and instruments
drive by
pretty
thought
easily. This is basically a MIDI
using EEG,
instrument, so
or electroencephalogram.
you could have any voice you want. Could be
So
could be
it's
human
a novel
voice. It
musical
could be.
instrument. It generates notes from conscious control without
And since we have
movement.
6 pitches, I
was
can
moving
switch
there,
the
but I'll
keys well. They're major
explain
key,
what that was
minor key,
about.
what have you.
It uses EEG, electroencephalogram, and it uses intentional control. It's not just passively
Moving
generated.
your right hand, your left hand, that sort of.
There's the motor cortex, and it's thinking about movement, and you have to specifically think about one side.
Their thoughts.
It's lateralized. So in this, and then there's visual. There's the visual cortex. I use the visual cortex in this one. So this is just a piano sound, obviously, and now we're in a major key. The minor key before. There'll be one more, I think. When the visual cortex is activated, that alpha frequency goes away. So when you open your eyes, it goes away. When you close your eyes, it goes up. So the relative power of that. So opening and closing your eyes is the basic idea, but you can so the top and the bottom are very easy, meaning the top of the scale and the bottom of the scale are related to the power. So you can hit the top and the bottom quite easily. Going in between is more difficult, but I'm learning more and more how to control the middle. So I can dip into the middle and come back out by partially closing and coming back out.
Moving and not moving if it's somewhere in the middle.
Right, exactly. And it's more difficult in the middle, but it's like any other musical instrument. When you're new, you're a bit sloppy and you get better with training. And I think that, like I said, the motivation of having music playing live is powerful enough that people will learn quite well, I think. So in this one, it's just a synthesized sound and it's in a minor key. In any case, I think you get the picture. Oh, whoops, I didn't mean to come out of the full screen mode. So then, where am I going with this? I don't know if anyone recognizes that film, but no.
City of Lost
City of Lost. There they were doing I think he was taking the souls out of kids, or he's taking their mind. It's like poor children. We're not planning that. But the future directions are musical. So within the musical paradigm, there are lots of ways to go with that. This one is chords, for example, switching between chords, not just notes. Switching between timbres. So you could switch, have a preset melody, and then you're switching instruments. You could trigger whole passages. But diagnostically, it could also be used for listening to EEG. In the hospital, we have heart monitors, and people are very attuned to changes in sound that let you know that the heart's going to arrhythmia. EEG is a little more complicated because you have 20 channels going at once, but you could learn to recognize certain patterns that might be useful, so you're not having to stare at the EEG continuously if you're doing continuous EEG. So it's more diagnostic. And then therapeutically, motor impaired patients with spinal cord injury, brainstem stroke, or ALS, they have motor disability, but their motor cortex is still intact for the most part. And that part of their brain is not being used much, or it's very impaired in its ability to effectuate movement. Funny I say that. So I can then go and just hook them up to this device and have them be able to express themselves using part of the brain that they don't get to use much anymore because they're motor impaired. And two, I'm willing to believe that there'll be some cognitive rehab that may actually help flip back and help them with their motor disability. Now, if a person has a amputation, they're not getting movement back out of that arm. But patients with brainstem stroke essentially have an intact arm. They can't move it. They have an intact motor cortex. They're just missing a portion in between. It's like the wire's cut in the middle, and I could use this to bypass. Obviously, I'm creating music. I'm not creating movement, but we could work a paradigm where we're improving the use of that part of the brain, the cortex, in order to start getting them to move more. So I'm applying for grants for clinical trials to see what this does.
Is it considered ethical, assuming the person is fully cognizant of the risks, to go and do surgery on their motor cortex so you get better signals to control their arm? Because I would be,
yes.
I can use my arm, I would totally sign up for that.
Absolutely, yes. It is. I mean, obviously, it's exactly as you said. They need to be awake and competent, but a lot of these patients are fully cognizant. The classic would be a locked-in patient. They have a really bad brainstem stroke and they can't move at all. Cognitively, they're completely there. They have difficulty communicating, but those type of people, they would sign up for that. Again, the research isn't great, so we don't have a whole lot of data as to how this would work well invasively. Ironically enough, meaning going intracranially, we actually don't know very well what we'd be able to do. But yes, and there are trials. It's just the numbers are so tiny that we don't have good control yet with that. And but that is being actively pursued in general. Yeah.
You're basically, I mean, in your instrument, you're mapping one thought pattern onto the music.
Mm-hmm.
Obviously, other people are mapping it on the cursor control.
Right.
People are mapping it on whatever. So
Mm-hmm.
one claim is that because, probably evolutionary-wise, sort of the music things, we probably have more stuff going on around music than we do around moving cursors. We don't have a whole lot of evolution on that.
Exactly, and that's my theory as to why we'll do better.
Is there any other? Is that really the key difference, or is it? Or that raises other questions? Or what other?
What other modalities could you use that are powerful? Yeah. Well, tying it into emotion is helpful, and that limbic valence that music has, which meaning it's very emotional, is a motivator. So if other paradigms using non-musical things that are very emotional might work well.
So in your examples, I mean that's pretty amazing. The timing was very good.
Yeah, and I'm able to.
With 6 outputs, I guess.
Yeah.
So I'm wondering where do you feel like that starts to top off? And can
right now, 6 is about it. I started off with. It's a good question. A lot of people want to, how granular can you get? Can I do 100 units? No way. 0 and 1, the binary is piece of cake. I can hit that. I started off with 8 or 9 because it was 8 because it was a major scale with all the notes, and I got better with 6, just a little more. So, I can't tell you precisely, but it feels like it's pretty good around 6, and that's sort of maxing out 6 degrees of freedom.
Could you? I don't know what all the variables are. You've got what was it, like 20 electrodes?
Yeah.
And if you go up to 100 electrodes, does that help?
It doesn't really help because I'm only using a small part of the. I don't even need most of the electrodes to do this.
So there's no real obvious way to go from 6 to 20.
Cut the skull open. Get in there. Yeah.
But can you combine?
With training, maybe.
Can you combine the visual and motor cortex? So if it was like eyes are closing here and then motor cortex, I'm kind of imagining. I'm
trying that. It's a little bit like patting your head and rubbing your stomach. It's just,
oh really?
It's kind of you're kind of doing
a
few things at once. But yeah, it would be nice to have a non-motor control over phrasing over the on and off, because as you saw, right now it's just continually producing music notes. I'm at whatever 2 a second, and that's not very musical. So I use a pedal, but it would be nice to use a second control to pause or not.
What about the thing where they use infrared light going into the brain to look at different activity in the brain? That might get past some of the motor stuff anyway.
It could, and there are other modalities. Transcranial magnetic stimulation, or MEG. Magnetoencephalogram uses a magnetic field to measure indirectly electrical field. It's got much more spatial resolution, so much better. But it's a gigantic device that there's only a few of them in the world, and they're massive, and it requires supercooling, and so it's a technical limitation. EEG is practical. It's portable. I can take the whole thing anywhere.
Right.
What's that?
The infrared lights, that's not so hard to do, right?
Not too bad. It's a little more invasive. Not the infrared itself, but from what I understand, the preparation is a little more. But I'm not sure. It could possibly. There's another one would be just DC direct stimulation. You can use direct stimulation from DC and turn on and off. Yeah.
That's a different thing, yeah.
Yeah. Another one would be fMRI. That's real time, good control. Spatial resolution's good. Temporal resolution's not so great. I don't know about the infrared, honestly. I'd have to look into it more. Sorry, I think you.
So everyone's really curious about like how many different input points are there.
Right.
When we're talking about like there's motor, but there's also visual.
Mm-hmm.
That suggests you have 2 bands.
Mm-hmm.
I'm seeing that you're doing a mapping from input to pitch.
Yeah.
and you settled on a major minor scale.
Yeah.
So I'm wondering, do you guys have plans to extend that one to other pitch systems that use 5 or 6 notes?
Yeah.
So that this could be portable to other cultures?
Yeah.
That have different musical scale systems. And then the other thing is, are you interested in doing things that are not just pitch, which also would have the same effect, because pitch and harmony, I think, are biases of like the Western classical tradition, but a lot of other people have focused on other elements of music like texture or rhythmic structures and things like that.
Yeah. Yes, and I've mentioned one would be chords, another would be timbre, just switching instruments or passages, and definitely thought about other scale systems. I was looking into some Indian raga type of scales and other ones. One thing about pentatonic is not bad. There's some that are culturally similar, like the fifth is tonics and fifths are in every culture, and pentatonic is seen in almost every culture. But yeah, there's lots of applications that way. This is first iteration. I want to see this, I want to see this work in a way that I know. And yeah, I'm culturally biased from Western musical tradition that I was educated in. And then in terms of two sort of inputs, I'm generally not doing 2 at once. I'm doing one or the other. I'm not using the visual and motor cortex at the same time in general. We're experimenting with it, but I want to get one modality going really well, prove that it works well, see how high we can get the percentage accuracy, and then, in parallel, try these other things.
Sorry. So are your inputs analog or digital?
Analog to digital. I mean, that box I have. So you got analog inputs. It's just current, right? It goes into a. The EEG has its 19 outputs coming out, just voltage that's analog. That head box is an amplifier and a AD converter, so that's digital.
Sorry, I guess
and digital into a.
That's a bad way of asking that question. I'm sorry, I'm asking so many consecutive questions. Are you looking at a specific direction and that's coded to a specific note, or do you have to be, like on a violin, you have to be very precise with your intonation and the location so that you get the exact pitch that you want, as opposed to, say, a fretted instrument like a guitar where they're fixed by the location of the frets?
So I'm just looking at the power of a given amount of rhythm at a certain electrode, sort of buffered over about 1 second, or 500 milliseconds.
Fretting structure because it fixes where the
Yeah,
sounds are going to be.
yeah, they're restricted.
Yeah.
Right. It's not a continuous scale. It's restricted to units, and those units are. I calibrate your range. I have you go through your own personal range, and then I set bins basically, and I have 8 bins, and if you get within this power, from 0 to 200, you get 1. From 200 to 400, you get 2, and that's it. So, you can imagine if you're near the edge of one of those bins, it's not so accurate, right?
We're going to do maybe 1 or 2 more questions, and then maybe a little bit of time to talk after. So,
Yeah.
do you want to go with your?
It was just a
I don't
comment.
know, you guys.
Did you want to go, Besta?
It was just a comment on the FNES, because we work with FNES in our lab, and I was just going to say it's easy to put on, but it's hard when there's hair. So prefrontal cortex is much easier to measure.
Well, we can get through hair. I mean,
It's more comfortable.
Yeah, I mean, I use people with lots of hair, and there's a limit, but you can get through. Like your hair would be easy. I might be collaborating with Reggie Watts, and his hair is crazy. I was like, Reggie, I don't know.
I went with the infrared stuff.
Oh, right. Yeah.
So we
Okay.
work with that.
Okay. I thought you meant hair. Shaved head's great, but
Yeah, but FNES.
hair's not. A little bit of hair's not a problem.
Please don't shave Reggie Watts' hair.
What's that?
Don't shave Reggie Watts.
Hey, it's up to him.
So my question is, you're using a pentatonic scale, and I'm not a musical expert, but I think pentatonics are pretty forgiving.
Yeah.
If you were to insert, instead of one of the 6, you inserted something that sounded really horrible.
Yep.
Are you able to avoid hitting that note when you're controlling it?
I'm more and more, but you know, I'm cheating a little by doing a pentatonic scale.
Sure.
It sounds
And that makes
good all
sense
the time, you know. I realize that. And since the accuracy is not great in the middle, it's okay. It's getting better. I avoid, the pentatonic avoids the 4th, which sounds terrible against the 3rd, for example. And the 7th can sound really bad against the tonic. So I did cheat. And the control is not great to avoid a bad note. As we get better, I may flip it back and see if we can, you know, as the control gets better, we kind of prove scientifically that we have accuracy that's higher. Might try that because it would certainly be more interesting, a little more dangerous, which makes it interesting. Yeah.
So would you be able to insert some timing control with your eyes? Then, like I think you were sort of saying Lucia was doing that a while ago.
Yeah, he wasn't doing timing per se. He was just doing eyes open, eyes closed for control, the visual cortex, which is pretty much what I was doing there. You could do eye control and then do motor cortex for the scale, and then use your eyes for control.
I was actually thinking, is it possible to do that? You would still have to use the motor cortex for the tone. You couldn't do it all with the visual cortex and then use your blink for.
That's right. That would
notes.
clash.
Okay.
Yeah, that would clash. We are really limited in what we're able to use, as you can see. There's a reason it's not just, people have this concept of EEG, like you can just read your thoughts and then why don't you just translate that into a robot that does anything. You know, it's what I tried to say with the talk is describe all the difficulties, not to shoot it down, because I obviously love EEG, I find it really interesting, but it's very messy signal, and it's really difficult to weed out what's not even brain signal, and it's also difficult to weed out what we know is functional and what's not. So.
Were you seeing much crosstalk between the motor cortex and using the volume pedal?
No, and I mean I specifically put it on my left foot. If it were my hands, it might get you get a little bit bigger signal in the motor cortex with your hands than you do with your feet, and I put it on the left and not on the right for a reason. If I do use it with motor cortex and the foot pedal, it will affect things more in the motor cortex paradigm than it will with the visual cortex. The visual cortex doing that shouldn't really be a problem. You don't want to move much. If I move my upper body even much, you get messy signal. So I got to really detach that foot to keep it away. But yeah, it's very sensitive. So.
Okay, so I think that's about it. I want to thank you, Thomas. It's been great.
Thanks for having me.